Hey everyone, this is Will. Welcome to the 16th miniKanren uncourse Hangout. Before we begin, I just want to say a quick note about last week's Hangout, which was the 15th Hangout. We had a lot of fun, a lot of really cool stuff going on. There was one thing that I think I need to address, and someone afterwards, after the show, while watching the video on YouTube, pointed out that there was something in the background of one of the participants that was not safe for work, and that some people might find wasn't welcoming them to our hangout. So I took that seriously, and right now the video is private, and I'm going to go back through and see if I can maybe crop some of the video. Anyway, I wasn't sure exactly what to do, but I just want to make sure that this is a place where everyone can go and hang out and have fun, and that was just an accidental thing, I think, that we'll hopefully make sure it doesn't happen again. But anyway, I would just remind folks, please check, see what's in your background, and obviously we just want to all treat each other as well as possible and have a very welcoming, open environment. And I think we have so far. In fact, I think there's a super friendly group of people, and I'm always looking forward to it. This is one of the highlights of my week, is hanging out with these uncourses. So enough said. Hopefully I'll be able to put that video back up online soon. All right. Another sort of format issue. Well, okay. So the other thing, next thing I should say is there's no Hangout next week because I'm on spring break and I'm going to be in Los Angeles visiting my sister and my mom. I mean, I'm not a student, so spring break means different things to me. Spring break for me means I'm writing a paper, but I will be out of town next Sunday, so no Hangout then, but we'll get back into the Hangout game afterwards. And then the third thing is Orchid had something on Twitter asking about do we, how's kind of the basic format going, and now that we've been doing this a while, do we want to reconsider how we do things? And I've noticed the last couple of Hangouts we've done lots of cool live coding and pair programming. That stuff's really neat, and we've explored some pretty advanced topics in miniKanren. That stuff's all cool and fun. I guess I have sort of two concerns there. One is that the Hangouts have been getting longer and longer, right? So we've gotten up into a couple 4-hour Hangouts, and I think if you count some of the time we spent talking outside of the recorded broadcasts, like we got up to close to 5 hours one week recently. So I think that's a little long. It's a little long for me to sit in this uncomfortable chair, and it's a little long, I think, just for people in general. So I would like to keep the Hangouts to like 3 hours or max. If we go shorter, that's fine. But anyway, so that's one thing I'd like to be mindful of. And the other thing I'd like to be mindful of is that I want to be careful and make sure the Hangouts don't become just really advanced hacking that are that's only understood by a couple of people in the Hangouts. I don't mind if we do some hacking like that, but I think I want to make sure that at least part of the Hangout, preferably the beginning of each Hangout, is accessible to people who are new to miniKanren or just learning, or maybe don't have a really strong background in functional programming or whatever. Okay, so what I'm thinking would be good is to have a couple things in each Hangout. Maybe one would be something more introductory. It does, where we do some miniKanren programming, but we also talk about, okay, well, what's this about? What's the theory of this? So for today, for example, I was thinking about maybe doing something with type inference, and just talking about that. Maybe people aren't familiar with type inference, and just going over that, looking at some of the rules, implementing a simple type inferencer in miniKanren, and so forth. And hopefully that would also help, if we do more hacking on things like the the type system that Ambrose and Michael Ballantyne were working on, which is pretty advanced. If you don't know the basic type inference stuff, you're not going to be able to understand that at all. So have something more introductory, more accessible. Then maybe have some cool show and tell-ish stuff that may or may not be as accessible. And then if we want to do some like real open-ended live coding, and that doesn't have to be super hardcore either. I mean, that doesn't have to be on a topic that's particularly hard, right? So anyway, that's what I was thinking. All right, hey Ambrose, how's it going? All right, I'm gonna mute Ambrose because I hear him typing. Okay, Ambrose is furiously typing. Yes. Anyway, so that's yeah. Wow, you're okay. Anyway, that's what I was thinking. But if anyone has any other things that they'd like to see, please let me know, or you can share your thoughts right now. But I would like to keep a more accessible aspect also. Okay. All right. So that's all the meta stuff I have for today. What I was thinking about, as far as things we could talk about today, unless anyone wants to talk about other stuff, I was thinking about talking about type inference, like just basic type inference, and writing a simple type inferencer for a little subset of scheme. And then Ambrose is here. We might hack some on the more advanced type system, or maybe he can explain a little bit about his work on the type systems, make it more accessible. And then the other thing that I'd like to show off is a really, really cool program that we finally got working this week. And I want to, I posted it on Twitter. Some people have seen it, some people haven't. But I think it's really cool, and I think it's worth showing off to everyone. And in fact, I'll probably start with that because I think it's really neat. Really neat. Okay. So let's see if I can pull this up. Screen sharing here. All right. And I think, well, okay. Did I talk last week, or did we talk last week at all about pattern matching in miniKanren? About how we've been working on, or wanted to work on, a pattern matcher, like the racket pattern matcher in miniKanren? I don't remember if we had actually shown that off or implemented that at all. But in any case, we okay, mention it, but then go into detail. All right. So there's a GitHub repo on my GitHub account called Relational-interpreter-with-match. Okay, so this is, all right, I'm muting Ambrose again. That sound. Type. Okay, so this pattern matcher, which we can see in interp-match, so basically what we did was we added a match, like a pattern matcher, like we use that pmatch thing, right, when we were writing interpreters in Scheme. So we have something very similar. This is the racket syntax for match, or a subset of that. Okay, and if you want to look at sort of the grammar for that pattern matcher, we have something in the README. I've been working on this with Michael Ballantyne. This is just kind of an informal grammar for what we support. We don't support all of the pattern matching syntax for racket, but we support a subset, and that means that we can write a program in miniKanren and just pick up the code and run it in racket, and it just runs. Okay. All right. And once again, this is part of the relational interpreter, so we added the pattern matching to the relational interpreter. And I will show you. All right, this is the cool version. It doesn't have a very good name. Variadic lambda with OR tests. That's not a great name, but it's accurate, but that's not really what it's about. So let's just load this, and I'm going to show you a couple of cool things. Hearing background noise from someone. Oh, it's Cato? All right. All right. No worries. Okay, so yeah, so here we have an extension to the relational interpreter. We've extended our interpreter. You know, we've got a val expo. I think I've got a valo also. So let's just try this out real quick. And we've played around with the relational interpreter quite a bit, right? So valo doesn't take an environment. We can do something like lambda xx, and we get a closure back, right? And of course, we know we can put a fresh logic variable to represent the expression, and we can, you know, infer. Well, I probably want to change that for run star. So what do I do? Oh, I managed. Whoa, I really messed that up. That's impressive. Oh, I know what it did. Okay, sorry. Let me go back. Go back. Oh. My Emacs Kung Fu is not strong today.
Will, you want a hint?
Yeah, okay. Go ahead.
Bring up the thing that was failing.
Okay. That one?
See where you have your valo, that you have an extra paren too close to your...
Yeah. I'm just going to...
Sure, all right.
I'm just going to... Oh, whoa. Oh, yeah. Well, okay, so what I need to do is... whoops. That. I think that's right. Okay, good. All right, here I am fumbling around. In fact, you can see that now we can infer things that have a match expression. Okay, so we're matching on something which turns out to be a number, like we might match on 5, right? So that's the value. The expression we're matching is 5, and then we have a clause that has 5 here. So those would match, and then we are just going to evaluate the lambda expression, which would give us the closure. So that works. Okay. All right. So that's just the closure stuff. Okay. So what is interesting? Well, okay. So what's really interesting, of course, is that we have letrec in our language, right? So just as a refresher, or in case you haven't seen this before. We can express things like append. This is something Michael Valentine asked about. Can we run just append like in scheme or in racket, right? So we can do like if L, then return S. Else we're going to const the car of L onto the recursion of the coder of L onto S, and then in the body of the letrec, we can make a call to append of like abc.de, and that works, and that gives us abc.de, and we can even do a run star and all that good stuff. Okay. So what's cool here is that we're running just racket or scheme code in miniKanren in the relational interpreter of Valo. Okay, and of course, what's really cool about this, and I've talked about this a little bit before, is that we can now start putting logic variables in the call to append. And now we're treating it as a relation, and we can run it backwards. Okay, and we also saw that because we're in the context of a relational scheme interpreter, this is strictly more general than translating append into, say, the appendo relation or the sort of append that you would see in Prolog, because now we can actually generate arbitrary scheme expressions that evaluate to the list that we're looking for, ABC. And furthermore, if we want to restrict this to actually be a list, we just put a quote in front of there, and now there is only one answer, and that's sort of recaptured the behavior of our appendo relation that we normally show. Okay, so we have this idea, and of course, I think there was another trick which I think I showed, which is we can do things now like, we can actually put a logic variable in place of append, right? And if we try to furry it, the miniKanren sort of cheats and gives us this function that takes any number of arguments, just returns A, B, C, D, E, and we can keep miniKanren from cheating by using an absento constraint, saying that the symbol A can't appear in the expression we care about, and now it actually works. It gives us the real append, and we can play all these fun games. And then the other thing we can do is we can actually put in a logic variable inside the definition of append itself. Like that used to be S, and we can get an S back, and if we do a run2, then I think it cheats again. Yeah, it gives a quote DE. So we can play all these sorts of games, right? So we're more general than we were when we wrote appendo as a relation in miniKanren. All right, that's cool. Well, so Michael Ballantyne and I were talking about what sort of really cool programs could you sort of write in a style, where you're just taking scheme code or racket code and running it, right, and treating it as a relation. And of course, one great advantage of this approach is you don't really have to understand miniKanren to do relational programming now. You can just write scheme or racket code. You can take existing racket code, for example, and just use it, and just put logic variables where you want to infer things. Okay, it's slower than writing appendo because we're under a level of interpretation with the valo, but it's more flexible in some ways. Has a different set of trade-offs, but the coolest thing is this is just racket code, and we can or scheme code or whatever, right? And I can literally just take that code and I can run it directly in scheme, and I get back A, B, C, D, E. And in fact, that's even useful for debugging. I found this is very nice for debugging code because I can just run it in racket or run it in scheme. Okay, so that's the basic idea, is that we can just take scheme code or racket code and run it either forward as a function in the relational interpreter or put logic variables wherever we please, treat as a relation. Now, in practice, if you really want to write more sophisticated programs, like a relational interpreter, or say you want to write a scheme interpreter inside of scheme, inside of this relational interpreter, or something that's really much more complicated than just append, this approach gets a little tricky. Because when you want to start inferring arguments by putting logic variables, in this position, for example, this Q here, once you start inferring things like that, then you have to be a little careful because, once you started adding variables everywhere, miniKanren is free to sort of cheat again. We saw some examples of miniKanren, cheating in a way, trying to find like the simplest, stupidest example or code that would do what we asked for. Not, it's not really cheating; it's doing exactly what we asked for, but we weren't being smart enough to tell miniKanren what answers we want. But if you write something like a scheme interpreter in this style, if we wanted to write like an eval in scheme this way or in racket this way, if you don't have pattern matching, if you don't have something like the p-match pattern matcher we were using before, it gets really awkward because what you have to do is for each clause, like for the lambda clause, you have to use a bunch of ifs and cars and coulders and break apart the expression coming in. That's a lambda expression, and you have to check that the first thing in the list is the lambda symbol. If it just to make this more concrete, if the expression we're matching against is like lambda x body or something like that, right? If we're matching against a lambda expression in a pattern matcher, we could have the pattern look something like this. With pmatch, we'd have the back quote gone, or we would just remove that. But so let's see. In pmatch, if we were matching against an expression, we would say something like this. Here's an expression, and here's one of our clauses, and the pattern in this case is lambda x body. And those commas mean that those are basically variables. We can match against the x, whatever the x is against. So if we say pmatch, lambda yy, right? Then the variable x will be bound to the symbol y, and body will be bound to this y, and so forth. And then those variables we bound, we can do whatever we want in the body. And so if we have pattern matching, it becomes a lot easier. So we're enforcing through the pattern matching the structure that this is a list, that the first element in the list is the symbol lambda. The second thing in the list is itself a list, right? And in fact, we could even do things like have a guard that x is a symbol, things like that, right? And so we can make sure that the lambda expression isn't too long, that the body is just one expression, and all these sorts of things. We can very easily enforce just from the pattern matching the structure of everything. Okay. If on the other hand we don't have pattern matching, then it becomes a lot more awkward, because then what we have to do is have like a cond or something like that, just like a regular scheme cond, or racket cond, or an if, or something like that. And then one of our clauses is going to be something like and equal, so say we have some expression expr coming in. If the car of expr is, quote, lambda, then it looks like it might be a lambda expression, but if we really want to ensure that we have the right structure, then we have to say the catter, which is the second thing in the expression, that's a list, and its length is 1, and all these things, and you end up with a whole bunch of special cases. And then accessing the x, accessing the body, you either have to let bind those, or it's, you're taking cars of cooters of cars and all this stuff. It gets really, really awkward. That's why we use pattern matching when writing things like interpreters. Okay, but when you're writing these programs in Scheme or Racket running under the relational interpreter, it becomes especially important, because if you don't enforce all of these properties, like that the catter is a list or whatever, miniKanren will just leave a fresh logic variable in that place when you're running backwards. So in order to get the right structure, you actually have to do a lot of work, and it's extremely expensive, and the code is really verbose. It's much more verbose than writing it with explicit cars and cooters and equals in Scheme even, just because miniKanren is so, it's so happy to put logic variables wherever it wants. So that's really awkward. It's really awkward. So we don't want this. We don't want to have to explicitly do equals and cars and cooters, catters everywhere. We want to be able to use a pattern matching notation. Okay. So basically what we want to be able to write is something like something along the lines of define eval and lambda expr and some environment and then pmatch on the expr, and then have different clauses, something like that. Okay, so this is how we would write an evaluator just in Scheme. Let's say if we use the pmatch pattern matcher, we're going to do the same thing, except in Racket. In pmatch, we would write the pattern like this. It wouldn't have a backquote in front. And in Racket's match, we would put a backquote there. And instead of that guard thing, we can actually, there's a special syntax, which is symbol x. So you put it inline. You say that x is going to be a symbol. Okay? So anyway, it doesn't matter. It's just a different pattern matching syntax. But this makes it much succinct and more efficient, and actually enforces the patterns better when we want to write things like an evaluator. Okay, and I have done that. I have written a scheme interpreter or a racket interpreter, a subset of a racket interpreter in Racket using this approach, and I'll show that to you real quick. That's actually in different files. Variadic lambda with map tests, also a terrible name. But you can see what the interpreter looks like. So here is a scheme interpreter, or a Racket interpreter, written in Racket using the Racket pattern matching syntax. Okay, and you can see that we're using match on the expression, and we have all these nice patterns. And this runs. This runs just fine. It's slow, not surprisingly, but it does run. It's slow because when you're evaluating an expression, you're evaluating it under this interpreter in Racket, which is being evaluated under the relational Racket interpreter written in miniKanren, which is evaluated under miniKanren, which is being run in Scheme or Racket. So you have a lot of levels of interpretation going on. There are techniques to try to make that faster, but that's why it's slow. Stacks and stacks of interpreters. That's exactly right. Daniel asks, is it me, or is this a lot faster than the version you showed off first with the Y Combinator? It's probably a lot faster. The Y Combinator has a lot of overhead when you use that to define things in these interpreters, because then you have to interpret the Y Combinator over and over again, stuff like that. So yeah, I mean, I think this actually is faster. This approach is faster. So we've gotten better at writing these sorts of programs, and being able to write a program like this actually is nothing to scoff at, and we can add all sorts of things. I've added lists. Okay, here's one thing I did that was kind of interesting. I added map to the relational interpreter, but it turns out that's not necessary because you can also define map. You can define list otherwise. Other ways, you don't need map to define lists. You can use like a let rec and a let loop inside, which I did here, which is more verbose. You can also, I've got some version, I think, where I defined map. Yeah, so here's another version. So now that we're in this world where we can just write arbitrary scheme or Racket code, if I want map as a helper to define something like list evaluation, I can just define map as just like a scheme or Racket function. I don't need to build it into the relational interpreter. Okay, so this gives us a lot of flexibility. We can extend the language, extend the helpers, stuff like that, without actually extending the relational interpreter itself. Yeah, so this is a version of the relational interpreter that has quote and list and symbols and lambda and application. And of course, the reason I wanted that language was so I could do quines and I love you programs, and those work. They're slow. But I can actually generate quines with these interpreters now. So when I generate a quine or generate a I love you expression, we're actually, just using the scheme interpreter or the Racket interpreter now. We don't actually, someone had to go through the work, and it's kind of harder, tricky work, of writing the relational scheme or Racket interpreter. But once that's written, people can play all sorts of games inside of it. So I thought this was pretty cool. If we can show that we can write a full interpreter inside of the relational interpreter, that shows we can do a lot of things, because that shows we're Turing complete and all that. And it's sort of, the other cool thing about this to me is if you look at the implementation, we're using lambdas to represent our closures, our environments, and things like that. So we have a higher order implementation of this interpreter, even though the relational interpreter itself is first order, just has first order unification, data lists everywhere. So we actually become more expressive. We can do different encoding tricks because we have lambda now in lexical scope that's understood by the relational interpreter and so forth. So I thought that was cool, but when I was showing this to people last week, most of them were kind of underwhelmed. I think they were underwhelmed because maybe they don't play around with metacircular interpreters as much as I do, stuff like that. But but I think I understand why they didn't think this was as cool as I did, and it's because it's hard to tell what's happening in this interpreter at the scheme or racket level versus the meta interpreter written in miniKanren. So it doesn't look as impressive, maybe. So I was like, fine, what would be more impressive? And Michael Ballantyne had a cool suggestion. That's what I'm going to show you. So this is the thing I really want to show you. What we did was we took a little simple proof checker that Matt Might wrote, and it takes a proof in propositional logic. It's very simple logic, and it only has two rules. You can make assumptions, and you can use a rule called from logic called modus ponens, which is like an implication. That's like, if you know A and you know A implies B, then you can derive B from those rules. It doesn't matter so much about how this works. If you're not familiar with the theorem or with logic or modus ponens or whatever, no biggie. We can talk about that another time or whatever. But the main point to understand here is that, first of all, this is just a racket program. Okay, and we're using the pattern matcher in the proof question mark. But proof question mark or proof that really is just a racket primitive. And I can take this code, I can take this big letrec and just run it in racket, and it works fine. It gives me an answer, either hash T or hash F. Hash T means that we've proved a theorem. Hash F means that the proof didn't check. Okay, so we start out with the full proof, and we check to see if the proof is correct or not. And you can see that we use member question mark, the member predicate, in the definition of proof. And once again, we don't have to add member question mark to the relational interpreter. We can just define it in racket. Okay, and this runs forward. Here we're just running this as just like a function in racket. We're treating it just like a function. We have some big proof tree. We're trying to prove. Let's see. We're trying to prove C, given the assumptions A implies B, and B implies C. So it's just like a transitivity type proof. It doesn't matter. It's a silly, stupid proof, but the idea is the important part. Okay, so we have this little proof checker. And now what we're going to do that's interesting is we're going to take this proof checking function, and we're going to not change any of the racket definitions, but we're just going to change the call to the proof, like what we pass in. And in particular, instead of passing in the entire proof tree and just checking to see if it's correct, now we're going to put in logic variables for the assumptions and the antecedents and all that stuff. Now, the assumptions, we're actually going to say what they are. So here are the assumptions. A implies B, B implies C, and we're saying we want to prove C, but the thing that we're leaving out is we're leaving out the proof tree itself. We're not saying what the proof tree is. We're just saying, okay, those are logic variables, and we're just going to run this function, this racket function, with fresh logic variables in parts of the proof tree, and we have a hash T here saying that we want the proof to be true. We want it to check. And we get back the entire proof tree. So we didn't include any of the modus ponens or the assumption parts in general. We certainly didn't include the modus ponens rules. What we've just done is we've taken our proof checker and we've turned the proof checker into a theorem prover just by putting logic variables in certain places. And this idea, in theory at least, could be scaled up to a much more sophisticated theorem prover, for like all of first order logic or whatever. But the key idea is that we're just taking a racket function, in some senses a non-trivial racket function. We're using pattern matching. We've got helper functions that we're defining to use and stuff like that. It's doing an interesting job, which is proof checking. And now we can just, by putting some logic variables in the right place, turn it into a theorem prover and make it do more work than it was ever intended to do. And in fact, this code existed. This is not code that I took and or wrote or Matt Might wrote intended to run this Racket code as a relation. This was just Racket code he wrote to run in Racket. And the idea was that we could translate this, to miniKanren somehow, and we actually were able to do that. But now we've shown you don't actually have to translate it to miniKanren. Yeah. So that's what I've been playing around with recently. So I think we're actually at the point now, and certainly it would be better if we could speed everything up. But we're already at the point now where we can start running real Racket programs forward as functions and test things out by just running them in Racket, make sure they work, and then treating them as relations by putting logic variables different places. Obviously, you have a couple trade-offs. The biggest trade-off probably is speed. It definitely slows it down. There are some techniques to try to make it faster that we're not doing right now. There'll be some work to make it much faster. Another trade-off is you lose some control, because you're really relying on the relational interpreter to be written in a smart way, and if it's not, then your program might go into an infinite loop in certain cases and things like that. But it's also more general. You can put logic variables anywhere, including in the code. So it's a very interesting approach to relational programming, I think, and that's what this paper we're working on is about. Let's see. Nahal asks, would you mind explaining why you call it variadic? Yeah. So do we return? Do we apply? Or sorry, do they talk about variadic in this? Oh yeah. Okay. Interpreter of variadic lambda. Okay. So in Scheme, you can define a function of 3 arguments like x, y, z, right? And we could sum up x, y, and z. And this is a function or procedure. Whoops, x, y, z. This is a procedure of 3 arguments, right? So we have to make sure that when we do a procedure application, we really do feed in 3 arguments like 3, 4, 5. Okay. So this is a fixed arity function. The arity, or the number of expected arguments, is fixed, exactly 3. Another thing we can do in miniKanren is just say lambda x, and now x will be bound to a list of the arguments, right? And if we do lambda xx, we'll get back to list 3, 4, 5. In fact, that's the definition of list in Scheme, or one way to implement list in Scheme is just lambda xx. But we could also do something like lambda x length of x, and now it'll give us the length of the list. So if I want to pass in more arguments, we'll get the length of the list. Or because x is a list, I could do something like apply plus to the list and add them all up. Okay, so that's a variadic function. So a function can take any number of arguments, and this version of the relational interpreter supports variadic functions. And so we can actually do these sorts of games in Scheme, in Racket, in the relational interpreter now. Nahal asks, is that so you can just copy and paste existing code easily? Not really. I mean, most of the code you see for Scheme isn't variadic. And you can write helpers to try to get around some of the variadic stuff. It's more like, well, I had specific use cases in mind. The first paper written on miniKanren, which I wrote with Dan Friedman in 2006, it had all sorts of ideas about writing relational variadic programs. What sort of things could you do if x is a logic variable or things like that? And those turned out to be things I didn't know how to do in Scheme very well. When you have just miniKanren running in Scheme, but once you can run things in the relational interpreter, then it's fine. So, for example, I wanted to do things like in Scheme have a variadic function and infer. You have a logic variable representing like all of these arguments coming in, or things like that. Run the code backwards that way. But the problem was I could never figure out how to do that in in Scheme because Scheme doesn't know about logic variables. So I couldn't get that to work. But once we're in the relational interpreter world, then this stuff does work. So, I mean, I've got actually a whole another repo showing all these sorts of examples with variadic functions. Where's that one? I don't even think it's this one. I think it's somewhere else actually. Yeah, because this is the one with match. Let's see. Yeah, I've got a lot of these repos now. I haven't even gotten a chance to show them all off to everyone. I'll have to maybe it's in here. I need to organize these things a little bit. Here we go. Interpret variadic lambda tests. Yeah. Maybe this one isn't. I don't know if I've checked this one in or not. I need to clean it up if I'm going to check it in. But yeah, so I've got somewhere I've got a zillion tests from the paper that I originally wrote, showing how to do all sorts of interesting tricks with variadic lambdas. Oh yeah, by the way, this is what a scheme interpreter looks like with quote and cons and lambda and application and variables. This is what the Quines generating interpreter, or the Quines handling like scheme or racket interpreter looks like if you don't have pattern matching. It's really, really nasty. So you really want the pattern matching. In fact, this one's not even right. I don't think this one's sufficient enough to fully give the shape to all of the things like the lambda expressions. Yeah, yikes. Orca says, someone should make a Twitter bot that generates a new I love you program each time someone asks. Yeah, I guess, well, I was realizing I've got 1 million of those programs now, and I taught a class recently that had like 50 students in it, and it's like, oh yeah, you know, anyone wants some I love you programs, I'll give each of you like 20,000 or whatever. Yeah, actually, most of the I love you programs are well, I don't know. If you use the lambda character, I think they'd be less than 140 characters, but I'm not sure. If you left out the side constraints, I think they'd be pretty short. Anyway, that went on a little longer than I intended, but I was trying to give the background. So just to recap, we've gotten to the point with the relational interpreters that we can run, you know, sort of non-trivial scheme functions now. You know, not giant programs, obviously, but things like interpreter that's Turing complete, things like proof checkers, programs that use helpers that are also defined in Scheme or Racket. You know, pattern matching, variadic functions, application. We can do set bang now. We can do all sorts of things like that. So we can handle a pretty beefy subset of Scheme. So it's pretty expressive. Pretty expressive now. And one of the cool things, I mean, there are several advantages to doing relational programming in this way. One is, if anyone knows Scheme or Racket, or functional programming, they don't have to learn all of the miniKanren, or they don't have to learn all of Prolog or whatever in order to start writing programs as relations. Right? They can just take their functions, and they might have to massage them a little bit to handle the exact language of the interpreter, but the interpreters we're writing are pretty rich now, so it's not a big deal. And they can just take those functions and make sure that they work in Racket or Scheme, and then put variables wherever they want. So that's pretty cool. And I think it's a good way to show people what relational programming is about. You know, it's a little hard if someone doesn't really know logic programming or whatever. It's hard to give a very short demo of showing how this stuff works. But now I think it's a lot easier, and hopefully it'll be easier for people to try to imagine what something would look like when you treat it as a relation. And also, you don't have to worry about negation. You don't have to worry about the ordering of goal or the clauses and things like that. I mean, it just, you know, basically you're dependent upon the relational interpreter written in miniKanren to do that in a good way. Okay, and if it doesn't handle it in a good way, well, then you're probably in trouble. But as we get better and better at writing relational interpreters, hopefully these programs will just get better and better. And the other thing is, as we speed up miniKanren, as we improve miniKanren search, cut off infinite loops in certain cases, things like that, then all these programs will inherit from that as well. Orchid asks, is the main way to make relational interpreters fast partial evaluation? I think that's one way, and it's an important way, but it's definitely not the only way. In fact, it may not even be the most important way. I think it's probably not the most important way. Other things that are really important, we know we can do better with the search. Changing miniKanren's underlying search. So in particular, things like sort of like backjumping from set solving, where you can cut off certain infinite loops, where you know you're going to keep hitting the same condition over and over again and fail because of that. If once we can start cutting off infinite loops that miniKanren right now will always hit, even if you write it by hand, like a Pendo or whatever, that would be a big deal. So better search, partial evaluation. There are all sorts of program evaluation, static analysis things we can do to replace unifications with pattern matching, or we could even, in some cases, based on like a mode analysis, probably take an entire relation and translate it into just a function if we know it's just running in one mode, like in the forward mode, like Mercury does. So I think there are a lot of things we could do. Now, in some sense, that's a form of partial evaluation, I guess. But I think it goes beyond what most people think of partial evaluation. Yeah, we got a lot of tricks. And of course, there's all the parallelization stuff, right? I mean, these programs are inherently parallelizable because everything's pure. There's no sharing between the clauses or anything like that. So, fine-grained parallelism is tricky because the unifications aren't doing that much work, stuff like that. But if you just unnest the top-level query, a few levels, and then send each of those to a processor, even if it's not load balanced, even if some of the processors just do work for 1/10 of a second and then quit, that unwrapping seems to speed things up. Sometimes I do that by hand. I hand parallelize these queries in kind of a dumb way, but that'd be nice to automate. So there are a lot of things we can do. And apparently the sat solvers, they sped up by a factor like 1,000,000 over a decade or so by using some of these algorithmic techniques like backjumping to improve the search. So if you took all of these techniques together and used them, I wouldn't be surprised over the next, within 10 years, I would expect miniKanren to be like 1,000,000 times faster, or these queries to run 1,000,000 times faster, or something like that. In fact, I'd be a little disappointed if they only ran 1,000,000 times faster if we really concentrate on performance. Just because also you have improvements in hardware and things like that. So being able to run these queries on like a cluster and do some of these aggressive optimizations and neat tricks, that would be really cool. And if these queries ran, even 10,000 times faster, which I think wouldn't be that hard, then it becomes less of. I mean, it's already really cool, and it's somewhat. I think there probably are some cases where it's useful already, but if you make it much faster and cut off some infinite loops, then I think it becomes, really interesting. Really interesting. Orchid wants to make a really fast Kanren, but it's not sure how. Well, I do know some ways to make it faster. We could definitely talk about that. So Michael Ballantyne's working on trying to make the backjumping work. I would probably start with the partial evaluation stuff and some of the static analysis. But miniKanren is so stupid right now. You just have to make a less stupid miniKanren, and you'd make a lot of progress. So one theory I have, by the way, is that what's happening sometimes when you do these queries is that because miniKanren can handle infinite loops, like it just, it's basically doing time sharing among different parts of your program. I think probably what happens is miniKanren's just spending more and more of its time in various infinite loops that it can't cut off, just kind of starving out other computations. So if we can get better at cutting off infinite loops that we don't really need to run into, we should be able to do much better. Like just stupid things like, as a human, it's often really obvious how to reorder the goals dependent on what the arguments are coming in. You could even do that dynamically in some cases, right? Just like, okay, when you hit a goal, look at what the ground the status of the arguments are coming in, and then dynamically reorder some of the clauses, right? Stuff like that. And that probably would have a fair amount of overhead, but if you can cut off a number of infinite loops, that probably pays off in the long run. Let's see. Okay, so Orchid implemented persistent union find that Daniel mentioned. I'm not sure how to use it for unification, though. And Daniel implemented also. Wow. So we have Daniel implemented closure. Orchid, did you do it in Scheme or what language you use? Yeah, for R7 or Scheme. Okay, cool. So persistent union find. Okay, so the version I'm showing you is running in Vicari, which is a relatively fast scheme, but it's using association lists for everything, right? And we know the association lists are 4 to 5 times slower than using persistent data structures like hash maps, persistent hash maps. So you could already speed those times up by a factor of 4 to 5 just by using data structures that aren't completely naive, right? So there are a bunch of really low-hanging fruit. In fact, we've seen that, right, with Veneer. Veneer is using better data structures, and that's why that's why that even though it's not a full optimizing compiler doing all the sorts of tricks that Vicari is doing, not that Vicari is doing all the tricks, but Veneer can beat Vicari in some cases, which is really impressive, actually. That's really impressive. Okay, so let's see. I started to use Larceny, which is so fast compared to what I'm used to. Yeah, so Vicari, Larceny, Shea, these sort of traditional compilers, they can do lots of work up front. Yeah. Okay. So anyway, that's something I wanted to show you all because I was just very excited about this idea of what can we do just by taking a racket function and running it as a relation. And there are all sorts of things like what sort of programs could we write this way? I think there are lots of really interesting programs that we could experiment with just by taking the racket code and or the scheme code and see if we can see what interesting things happen when we treat it as a relation without changing any of the code. I've got a whole bunch of examples of things that we could try in that area. So I think we've just sort of scratched the surface. Okay, yeah. So Daniel's got a gist of at least partial implementation of persistent union find and closure. Very cool. Very cool. Oh yeah, and there are also other things that we have to add, like well, tabling in some cases could cut things off. We have to make tabling faster. But another thing we could add is things like the tree automata-based like grammar constraints or whatever, or type constraints, whatever you want to call them. That also could cut off searches in some cases. Okay. So, does anyone have anything else they want to show off, or shall we do some hacking on like a little type inferencer and kind of go through what that's about? Or do we want to look at the persistent union find, or what? What do folks? What shall we do? No comment. All right. So, does anyone have information on how to use persistent union find for unification? It's a good question. I know Dan Friedman has thought about this a bit. Daniel says the original paper was using mutable references, persistent array structures. Okay, yeah. I have not played around with the persistent union find for unification, so I'm not I'm not sure. But I know Dan Friedman has done some work along that lines. Hmm. All right. Well, sounds like Orchid and Daniel have some things to talk about there. I don't really have anything to add there unless anyone else knows about the persistent unifying, how you'd use that. Um, all right. Well, I'll let you all keep talking about that then in the chat, and let's take a look at type inference. Let's write a little type inferencer for like a subset of scheme or racket, and see how that works. If you haven't seen how to write a type inferencer, if you haven't seen how the typing rules work, it's kind of cool. And turns out relational programming is a good match for at least some of these type inference problems. So we can just go ahead and write a little type inferencer. And also maybe we can look at a little bit of what the mathy rules look like, because you see those in books and papers and things like that. And I found those really intimidating. Sometimes they're still intimidating because the rules can get really complicated, but at least the simple rules, if you understand how you write the interpreters, you can look at the rules and say, oh, that's just like a little program. It's something you can type in and get it to work. And to me, that helped a lot with my understanding of how these things work. And by the way, one thing that would be really cool would be to take just a type checker written in Racket, let's say, and turn that into a type inferencer by running it in the relational interpreter. Yeah, so there's like a simple type checker. A lot of times the type inferencers use unification explicitly, so I'm not sure about the type checkers. I have never really written just like a type checker. Everything I've written, because it's been in miniKanren, this is like easier to do a type inferencer than a type checker probably in miniKanren. It's kind of weird, but anyway. All right, so let's try doing some typing stuff. Probably everyone here has at least some experience with a language that has, well, okay, these are fighting words as soon as I start talking about types. The terms like static typing, people argue about whether such thing exists or what it means or whatever, and whether that scheme is statically typed or stuff like that. Let's just say that in a scheme program, you can get an error at runtime because of the types not matching, right? Like you could try adding, instead of trying adding a number, you could try accidentally adding a Boolean in a number or something like that and getting an error from plus, the addition function, right? So you can get a type error at runtime, whereas some languages like ML, well, actually going back something simpler than that, like a language like Java that has a type system and a type checker, you know, the compiler is going to try to find those sorts of errors for you before you run the program. In fact, it'll give you a compile error in certain cases. Now, a lot of these type systems, you can kind of get around things through unsafe operations, okay? But the compiler can legitimately find cases where you will certainly get an error or can't prove that your code will run without an error, and you'll get some sort of type error. And I think most programmers who've been programming a while have used at least one language that could give them a type error from the compiler, let's say. Okay? And I think we're all familiar with getting a type error at runtime when we try doing something like adding a number to something that's not a number. Of course, some systems will try to take the thing that's not a number and turn it into a number or whatever, various ways of coercion. So there are languages that can do type checking. Languages like Java. C can do type checking, right? That you can get, you know, C compiler will give you certain types of errors, even though it's not particularly strong type system. And let's see. Well, that's right? C is going to complain about certain things. Certainly, C++ is going to complain about things. Java is going to complain about things. Scala will complain about things. ML, Haskell. Some of these languages have what's called type inference. C tries but doesn't do too well. Yes, that's a good way to put it. Some languages have something called type inference, because part of the problem about type checking is that you have to write down the types so the compiler can check them. right? How is it going to check the types if it doesn't know what the types are? Well, if you're coming from a miniKanren or relational standpoint, like we kind of know the answer to that one, but you figure out the types. But in many languages like Java, you have to write the types down, and it can be awkward. It can make your code longer. You can get these type errors. There are times where the system should be able to tell what you're doing type-wise, but can't. So it makes more work for the human. Orchid points out that larceny, which is a scheme compiler, can give me errors when I call a function with the wrong number of arguments. Shea scheme can do that also. It's a basic form of type checking, maybe. Yeah, it's or like a very lightweight static analysis. Yeah, so even like a language like Scheme can have some amount of type checking, maybe. But in general, we think of Scheme as not really doing type checking. It's certainly not required. And Scheme interpreters in general aren't going to do type checking. So a language like Java, a language like C++, you're going to have to write down the types, and it's going to do some checking. And it's going to give you an error, maybe. The compiler might give you an error. Another approach is what's called type inference, where your program still has to be well typed. Okay, all the types have to match. You're not allowed to add a number to something that's like a Boolean, that kind of thing. But you're not required to write the types down. The type inferencer, which is usually part of the compiler, is going to try to figure out what the types are that make sense. And it's not going to know what the types are initially, but it will figure out, it will infer, it will logically, there are logical rules to tell it what the types are that would make sense. And so there are these type inference systems. Henley-Milner is probably the most famous, that can actually figure out the types from the program without having to write down the types. Okay, and this is really cool because it means that you as a programmer don't have to spend the time writing down the types. But usually there's some tools where at the command line or whatever you can figure out the type of anything you want. Okay, you can often write down the types and those will be checked against the types that were inferred, that kind of thing. But you don't have to write it down if you don't want. And in some languages, it will do sort of partial or local type inference, where some of the types you have to write down, and then some of the types the system can infer. Okay. In fact, even in C++ now, there is some sort of type inference that works, and it's very useful to have that. Okay, and Scala has type inference, ML has type inference. So having a language of type inference is really nice. So how do you write a type inferencer? I mean, it seems like magic. I mean, writing a type checker, well, if you know that you're adding x and y, and x is an int, and y is an int, well, that doesn't sound too hard to check that as a compiler. But if you don't know what x and y are, and then you have to figure out that those are ints, or could be ints, or whatever, or have to be ints, that sounds like a more complicated problem. So let's figure out, how do you write a type inferencer? Well, let's do it. Okay, so I'm going to screen share here. I'll do my desktop. All right. So let's look. Yay. Okay, Twitter. Let's look at some typing rules. So here are some typing rules for lambda calculus. We're really going to look at a subset of scheme, so call by value lambda calculus. Okay. So the lambda calculus, which we've talked about a little bit before, has 3 types of rules, and these are sort of the core of a language like Scheme or a language like Haskell or Clojure. The lambda calculus is the core of it. And we have 3 types of expressions. We have variables. We have what's called abstraction, which is just lambda terms, or lambda extractions, and we have application, which is like procedure application, right? So we have expression E1 applied to E2. That is an application. We have an abstraction would be like lambda xe, and then a variable is just like x. We're just looking up x. Okay. And we've got these mathy, logic-y rules. They're called inference rules that are written down. They tell us what to do for a type inferencer when we see different types of expressions. Okay. And because we're coming from sort of a tradition of logic when we write down these inference rules, we've got a bunch of mathy symbols. We've got some Greek symbols and things like that, and it can look intimidating how to read these things. Not a minute I gave a talk at ClojureConf on from Greek to Clojure, where we talk about how to read some of these rules, and we write like a little type inferencer. But it's not that hard for these sorts of rules. The main thing to understand is just kind of the structure of the rules. You've got a couple different parts. So first of all, you have the expression that you're looking at, like the lambda xe, and then to the right of that you get a colon, and then to the right of the colon is the type. Okay, so this is the type we're getting t1 arrow t2. For variable, the type is t, and for application, the type is t. Okay, now we don't know what the t's are. It's going to depend on the value, but the thing to the right of the colon is the type. The thing to the left of the colon is the expression, and we can think we're like pattern matching against the expression. Okay. And then we have this weird-looking symbol, which is called turnstile. That just means that we can infer that x has this type, or we can infer that lambda xe has this type, or whatever. Okay, so that's like the infers or derives symbol. And then all the way on the very left, we have this uppercase Greek gamma letter, which is the type environment. And this is very similar to the environments that we have in an environment passing interpreter, which we've looked at before. Basically, in the environment passing interpreter, an environment maps a variable, like x, onto a value, like 5. In the type environment, a typing context gamma would map a variable like x onto a type. So instead of mapping x onto the value 5 like you would in an environment, you would map x onto a type like int or integer. Okay. And the types we have here, basically the only values we have in this language are lambdas. So we're going to end up with these arrow types. So some value coming in goes to some value coming out. So you can think of the t1 as the value associated with the variable x, and the t2 is the value associated with the body e, that expression e, if x is bound to t1. Okay, so if x is bound to t1, then the body has type t2. That's basically what this rule is saying. Here we're saying if we want to find the type of x in some typing context gamma or some type environment gamma, basically we just look up x in gamma, and we will find that x has type t, and then the type t is what we return. So this is just an environment lookup. This is like looking up x in a hash map or something. Just looking up, or association list. This is just looking up x in a data structure, basically, if you want to think of it from a programmer standpoint. For the application rule, in order to do a procedure application, we better have a procedure on the left-hand side. E1 had better be a procedure. So this rule is going to be recursive. We're going to have to figure out the type of E1 and figure out the type of E2, those sub-expressions. The type of E1 has to be the type of a lambda, has to be a procedure. So we know a lambda has type T1 to T2, so therefore E1 also has to have some arrow type, some type coming in, T1, going to some other type. And furthermore, we know that E2 is going to have a particular type. It's because the value of E2 is going to be fed into this function for E1, they have to match. So the type of E2 is going to be the type of the argument coming into E1. So basically, this X thing, that formal parameter, that's going to have type T1. Well, what gets fed into this X? Well, what gets fed into the X variable, gets bound to X, is the value of E2, which is the argument coming in for the procedure call. So we know E1 because it has to be represent a procedure. That has to be an arrow type, and we know E2 has to match the first argument to the arrow type. And furthermore, whenever we take this arrow type and pass in the value of E2, bind it to X basically in the type environment, we're going to end up evaluating E and getting this output type. And that output type T is the type of the entire application. And then the only other thing to look at is, for this lambda clause, when we evaluate this, we're basically making an assumption. We're adding an assumption or adding a binding to the typing environment or typing context that X is bound to T1. X has type T1. And then and only then are we able to infer what the type of the body of the lambda is. This is actually the interesting part right here, this extension, because this is a little bit of make-believe. This is why miniKanren is useful for writing these sorts of inferencers. We actually don't know what X's type is until the procedure application happens down here, in this case. So if we just have a lambda, we don't know what T1 is. It's an unknown value that hopefully will be filled in later. So we're extending the environment with a binding between X, which is a variable. We know what that identifier is, but we don't know what T1 is. So that's like basically a logic variable. And then maybe that will be filled in later if we have a procedure application. Okay, so this is a little bit of make-believe. We don't know what the type T1 is. That's something that we can use with the logic variable to represent. Okay, so those are the rules for type inference. And we're going to implement those rules and see if we can write a little type inferencer. Okay, so before I do that, let me make sure for a second that I can look at chat and all that. All right, without the screen going wild. Okay. All right. So Orchid, do you see a problem with the typing rules, or is this you're talking about the cardinal or the other thing? In the var case, we have to take the rightmost X. Okay. Okay, so that's a good point. You're bringing up the shadowing thing. So it depends how we handle this environment extension, right? So this is just like the math, right? It's up to us how we decide to implement it, but you're right. When we do an environment lookup, if there happen to be multiple bindings for X, we need to make sure that we get the current binding of X. That's the closest in the lexical scope. That we handle shadowing of variables. So if we have lambda X, and then the body of that lambda is another lambda X, that kind of thing. Where if we have X's shadowing each other, we need to make sure when we look up X, we get the right thing. So that's something we're going to have to be careful when we implement it. If we really do treat this as a set, and we've, yeah, we just have to decide how we're going to implement this. So usually when you look at the rules, there are assumptions that are made that help you avoid issues of shadowing and variable binding and things like that. There are a whole bunch of conventions. There will probably be side conditions written down saying you need to handle this properly. So yes, we're going to have to decide how we want to implement all these things, how we're going to represent our typing context and so forth. And we better make sure we get our shadowing right. Absolutely. Yes. So once again, when I say that these are sort of the rules that you might see, depending on the book or the paper you're reading, they'll often either have or assume side conditions, right? That that you have to be careful of when you implement these things, right? So for example, if you read Barendrecht's book on lambda calculus, there's a convention that people call the Barendrecht convention, but he actually says it's due to someone else, where basically we're making an assumption that we've changed all of the variable names up front, so to avoid shadowing whenever possible, things like that. So there are various assumptions people make, or various ways to try to handle these issues. But it is a very serious issue. Like handling scope and shadowing and binding is really tricky, actually. That's the whole reason we have things like nominal logic and higher order abstract syntax and De Bruyne, notation, all that stuff. It's a very tricky problem. But yeah, we have to make sure when we look things up that we get the right variable. Absolutely, absolutely. Okay. Any other questions, or should we just try implementing it? All right, let's try implementing. All right, so I've got a little file that I started, infer.scm, and see if I can get the rules up here. All right. So let's define, I don't know, we could call it infer, we could call it turnstile. That's one way we tend to do this. I guess you could do a real Unicode turnstile. I'm just going to do bang dash. I don't think Scheme likes pipe. But okay, so that's usually how we write turnstile. So this is going to be our turnstile or inferencing relation. And this is going to be a function. This is going to look a lot like an interpreter, by the way. This is going to look a lot like an interpreter. Okay, so what arguments do we need to take? Well, if we look at one of the rules, we have a gamma. So turnstile is what we're defining. And the colon is just a separator, so that's not really an argument. But we can see we have three arguments. We have a gamma coming in, which is our type environment, or type context. We have an expression coming in that we want to give a type to, and then we have a type coming out. Okay, so we're going to have three arguments. So we're, we call it gamma. If we wanted to be really classy, we would do Unicodes or whatever. Unicode. We have some sort of expression, and then we have a type. So it's a three-argument relation. That's what we're defining. And we can use cond. I have a couple cases here. So if we want to have a case for each of those clauses, we're going to have three cond clauses. Are flowers like Nahal's Julia set up? Yes, yes. I'd like to see how Nahal would write this. I'm trembling. Okay, so we have three cases, and if we really wanted to, we could use a match E, which is like a pattern matching syntax. I'm not gonna do that, but we could. Now we're just gonna do a simple cond, and we're gonna have three cases. Okay, so the first case, and basically we're going to be looking at the expression type. If we pattern match, we'd pattern match against the expression just like we would in an interpreter. But they're basically three cases that we care about. One is the variable case. So that's when we have x. X is a variable, so that's our topmost case. And then we have another case where we're going to have an abstraction or a lambda. Abstraction is just a technical term for a lambda. So this is going to be the lambda case. And then we're going to have an application case. Okay. All right, so the variable case, so we have to decide how we're going to represent variables. We'll do it like we did in the interpreter. We'll say variables are symbols. Okay. Variables are symbols, so if we were writing an interpreter, we would do like symbol question mark or symbol ha. If we're just writing this in Scheme. But here we use a symbolo constraint to enforce that x is a symbol, expression is a symbol. Okay. And the reason we use symbolo is that if the expert comes in as a fresh logic variable, symbol question mark won't work right. It'll just give us an error. Actually, it'll just return false because the fact that our variables are represented as vectors. So we have to use a symbolo constraint, and if expert comes in as fresh variable, now it will be constrained and saying, okay, you have to be some symbol. Okay, so that's pattern matching against the symbol case. The lambda case, we're going to do something a little more structural. We're going to have to introduce some fresh variables. And we're going to unify the expert with the lambda expression. And I'll try to make it look similar to the expression here. So we have a lambda, xe. The commas are just saying that these are expressions to be evaluated. That's basically what we do with logic variables. So better introduce two new logic variables. So this is like a pattern matching type syntax, basically, and so we're saying the expression has to be a lambda. And if expression came in fresh, we'll succeed in this case, and it'll become a lambda. Right? So that's what it looks like for expression. And then similarly for application, we're going to have to do a call to equal. And in that case, we're going to have a call to equal, and we're going to say the expression, here we had an E1 applied to E2, E1 applied to E2. So those have to be logic variables, E1 and E2. Okay. And it's important to note that these clauses do not overlap. In Scheme or in Racket or in Lambda Calculus, application is not tagged. There isn't a special app tag or anything like that. So the fact that our lambda expressions are lists of length 3 and our applications are lists of length 2 is important. If our applications could overlap with lambda, then we'd have to be careful and make sure that we're not confusing our lambdas and applications. And we have some techniques for dealing with that in the interpreters, but I'm not going to get into that right now. We'll just do it the simple way. Do it the simple way. Let's see, flowers rock analysis. Okay, so now what are we going to do? Well, now it's time to actually implement some of these rules. The simplest rule, well, I'd say the simplest rule is probably the variable rule. And we're just going to look up x in gamma and see what's bound to. So we're going to do a lookup just like we did an environment lookup. We're going to do a lookup. I'll call it lookup O. We're going to look up the expression in gamma, the type environment, and that's going to give us back the type. That's going to give us back the output type. Just like we would do for environment lookup for an interpreter. So let's go ahead and define lookup O, which is easy to define. So we're going to look up x and gamma to get type. Actually, the easiest way to write this is very similar to what we do in an interpreter. We can just unify against gamma. And we have to decide how we're going to represent gamma. So the simplest way here is just like as an association list. We'll say y is bound to type T. Okay. And now we can have a conD, and we have two cases. So either x and y are the same, so we found in our association list the value we're looking up, which means that the type we're going to return is T, or x isn't y, that they're different, and that's when we use our disequality constraint, saying these two values have to be different, two terms have to be different. And in that case, we need to look up x in the rest of the environment, in the rest. So that means we're going to make a recursive call to lookup O. And return type. This is exactly the code that we would write for environment lookup in an interpreter if we want to use an association list. Exactly the same code. Okay? We could use literally the same lookup O for both. We might want to change the name, gamma to int or whatever, but it's the same code. All right. So that's our lookup case, and that's our variable case is done. And it also looks like the variable case in an interpreter. We just look up the value. Here the value happens to be a type, not something like a number, not a concrete number. Okay. So now let's look at the lambda case. Lambda case, all these rules are actually pretty simple. We have a lambda expression. Now we know that the type is going to be T1 arrow T2. That's the type. Okay, so let's just type it in. We have T1. I don't know. I guess the trickiest part is to decide where you put the type arrows in. Do you put it at the front or at the end? I'll put it in the middle. So we have a type T1 arrow T2. Now notice. We're trying to figure out what the overall type is. T1 and T2 are not the overall type. The overall type is T1 arrow T2. And we're going to have to make T1 and T2 logic variables. We don't know what those are. We don't know what their values are, what those types are yet. Well, that's no problem because we don't need to know things up front. We can just put logic variables in our place. Okay. Okay, and that's basically all the code below the line for this inference rule. And then what's the code above the line? It's saying that lambda xe in gamma, type environment gamma, has type T1 arrow T2 if we can prove that gamma extended with an association between x and T1, if in that extended environment we can infer that the body of the lambda, e, has type T2. That's how we read this inference rule. Okay? So what we're going to have to do is make a recursive call to gamma. We can see there's a recursive call to turnstile. This is going to be a call to turnstile. And we have some extended gamma, and then the second argument is going to be e, and then the third argument is T2. Okay, so the only thing we have to do is extend gamma here. And we could write a helper to do it, but because we just have association lists, it's actually not hard. We're going to take the old gamma, and we're going to extend it with a new pair in our association list, and that pair is going to be x bound to type T1. Okay. So T1 and T2 are fresh logic variables. We don't know what they are. We're going to figure it out, hopefully. The type inferencer will figure it out just by applying the rules, and hopefully there'll be an application, so we'll be able to figure it out for real. But the point is, we don't care. We just type in the math. We just have fresh logic variables everywhere that we don't know the values. That's fine. No problem. Let miniKanren do the work. We don't need to sweat about it at all. Okay, so we took care of the first two rules, and like Orchid pointed out, we need to make sure that we're very careful with handling our type environment gamma to make sure that when we look up x in our lookup case or variable case, that we're going to get the correct binding for x, the most recent association. So, we will get that with an association list. We're just extending gamma with a new association list. So if x is bound more than once, we will only get the most recent x because of this disequality constraint. This is the disequality constraint. This keeps us from looking further in the environment when we have multiple bindings of x. We'll only find the first x, and then we'll stop because of this disequality constraint. That's very important. If we don't have this disequality constraint, we'll get multiple answers back from lookup, and we won't just get the most recent environment. We'll get older bindings also. All right. So those are two of our rules, and we have one rule left. Okay, so we have the application rule. We're matching E1 against E2, or sorry, matching through unification against E1 applied to E2. It's fine. And this has two recursive rules. It's two recursive calls in this case. So here we're saying that if we recur using the same gamma, we're not extending gamma, on expression E1, we should get an arrow type. The arrow type T1 arrow T. Okay? T1 arrow T, and okay, well, what does that look like? Whoops. So that's going to look like T1 arrow, and I called it type instead of T. I don't know. Maybe we should change that, make it more consistent. I call this T. Okay. Now we got our T's going. Looks a little nicer, maybe. So T1 arrow T. That's T is our output type up here. It's the final type. So we're inferring that E1 in gamma has this type. That's the first recursive call. The second recursive call, we're going to say that in gamma, E2 has type T1. Okay. So T1 is a fresh logic variable. We need to make sure to add that up here. We don't know what its value is, but the inferencer should be able to figure it out. And that's it. So we have implemented the mathy rules, and as Orchid pointed out, we had to be careful with our environment representation to make sure that we're not looking things up, getting old, stale versions of variable bindings. But that's it. We had this little lookup helper because we have to look things up, and in math we don't really have to write that. And that's the entire definition. So now we should be able to actually run it. So this. Let's see if we can do some inference. Okay. Let's do a run one queue of turn style, and let's do in the empty environment gamma. Oh, sorry, yeah, gamma's first, right? Yeah, so gamma expression and then type. Okay, in the empty environment gamma, the empty association list, let us infer the type of lambda xx, which is the identity function. I'll call it lambda zz, just be fun. And let's figure out what the type is. And we can see we have an arrow type. Let me do a run star, prove there are no more types for that. Okay. And basically it's saying that we can have any type coming in, that's why it's a logic variable, any type to that type. Any type coming in maps to that type. That's the type of the identity function. Okay. Anything, arrow anything. That's basically what that's saying. We can also do something like an application. Okay, so of course, we can also type check something like just Z, and that won't type check because Z is in the empty environment. If we want to kind of mess around with the initial environment and give Z a type, we could say, even though we don't have int types, we could fake it. Now we've given Z a type. We started out with a type environment where Z was already bound to int arrow int. And now the variable Z has a type. And the reason we might want to do that is maybe we have built-ins into our language, right? Maybe we have things like 0 question mark in our language, and that's just a variable binding. And that's going to be int arrow bool as a built-in function, and now we can get the right type. So we might want to start out with a non-empty type environment. But if we go back to the empty environment, it's not going to type check. And then, of course, we can do things like applications. So we can do like lambda zz applied to, I don't know, lambda yy, that application, and sure enough, once again, we're getting back an identity function. Okay. To make this a little more interesting, one thing that we might want to do is do something like add numbers. So if the expression is a number, we might want to say that the type is an int, let's say. Okay. And what else can we do? We can also do something like, say, maybe we want to have, I don't know, addition. I think we talked about addition before. So we can say if the expression is an addition, of E1 to E2, those variables, then what are we going to do? Well, then we can just recur on E1 and gamma. That's going to give us some type T1. And then we can recur on E2, and that will give us a type T2. And what is it that we know about T1 and T2 in this case? You know, what are the types of E1 and E2 going to have to be? They're going to be numbers, yeah, exactly. Yeah, there's going to be numbers. So, you know, just like, because we're only going to be able to add numbers. So we're going to say it's going to be an int. Okay, and that's also right. We're going to say that the type of t is going to be an int. And if you noticed, I almost put the type t here, and then I decided to move it up. And the reason I moved it up, of course, is that these two calls to turnstile are recursive calls. Right? There could be infinitely many expressions or whatever, and I want to try to avoid going into infinite loops. So all my unifications are going to come before my recursive calls. But the nice thing about being able to say that E1 has to evaluate to an int is that if E1, you know, happens to be a lambda or something, then that will cut off the search immediately. It will cut off the inference. It will just fail. So that's useful. Another thing we could do, in addition to integers, we could do something like add booleans. So here we can explicitly enumerate them because there are only 2 Boolean values. So if our expression is true, then our type is bool. And similarly for an expression being false, is also Boolean. Okay. And let's see, what else should we do? Well, actually, let me make this subtraction instead of addition. Works just as well. Let me make one for multiplication, and we'll be able to do factorial actually in a minute. I have multiplication, and what else? We need if, right? So we need to be able to write if. And if we have an expression being called if E1, if E1, E2, E3, okay. So what is our, what's if going to look like? What do we know about the value, the type of E1, for example? Depends, actually, if we want to do scheme rules or, better typing rules. In scheme, E1 can evaluate to anything. But, if we want to be a little tighter, if we don't want to use scheme rules, we could tighten it up and do something like what you'd have in ML. And yeah, so we could do like Boolean. So so we could do a recursive call and say in gamma, E1 has to be a bool. Has to evaluate, or the type of E1 has to be a bool. And what about the types of E2 and E3? Do we know anything about those types? And once again, this depends on exactly what typing rules we want. That they're equal. Okay, so that is a very standard typing rule. This is something you would see in something like a Hindley-Milner or whatever, or like ML type system. We would enforce that E2 and E3, the different branches of the if, have to have the same type. Okay, so we could say that in gamma, E2 has the output type T, and also that E3 has the output type T, and that those are the same type. Okay. Yeah. So whether or not you want to make those the same type, well, that depends on the exact type system you're creating, but most type systems are going to require those two things to be the same. And then, if we really wanted to do something like factorial, we would probably have something like, 0 question mark of E and things like that. So if E, so what would the typing rules for 0 be? If E is going to, if we want to know if E is going to be 0, so what can we say about the output result or the okay, so the type of 0 is int arrow bool. Right? So 0 question mark is going to take an integer and it's going to return a Boolean value. So because of that, we know, first of all, that we're going to have to recur on E. And E had better, therefore, have the type int. If not, we want to fail. And furthermore, we know that the type going out of this entire thing is a bool. Okay. Once again, I'm going to reorder these two goals, so my unifications come before my recursions. And now you can see we're starting to get a reasonably rich, a type inferencer for a reasonably rich language. And you can also see that, for the primitives, these are pretty simple things. Like things like times, it's pretty obvious how you write these once you've seen a couple of these. Okay. And we also have some choices to what exactly we want to use for our typing rules. Okay. If we want to look at a book like Pierce's Types in Programming Languages or a paper, those papers will often have, typing rules like this for the subset of the language that they're talking about. So we could just go by those rules and type it in directly. But okay, so now let's just see if we can type check anything fun. Put it up. Okay, and let me see if I can I type check 5, for example? Yep, 5's an int. Hash T is a bool. What about plus 5 to plus 6, 7? That type check? Uh-oh. Something there's not right. Okay, let's try plus 5 to plus 6. Uh-oh. Oh, I got rid of plus. I did minus. That's it. Okay. I go back and add plus. There's no reason not to have it. Uh-oh. No, Emacs, don't do it. Don't do it. Don't do it, Emacs. Don't do it. All right, Emacs is about to go down, I think. Come on, Emacs. You had one job. All right. In there. All right, let's try this again. And let's load infer. That's once again return style of empty gamma and some expression like -3 -4 5, and let's see what the type is, and that's an int, sure enough. Okay, and we can play all those sorts of games. We could even define factorial, use the Y Combinator, give a type to factorial. That's cool because even though factorial could go in an infinite loop, we can still give it a type. We can still give it a type. That's neat. Okay, so what might we not be able to give a type to? Okay, so can we give a type to every legal scheme expression? Are there any legal, I mean, if we kept adding primitives and so forth, are there any expressions that we wouldn't be able to type? Try it backwards. Yes, we will try it backwards a second. This is a trick question. I feel it. Yes, it is a trick question, but it's a very, very important trick question. It's a very deep trick question. Running it backwards is also very deep. Okay, Orchid's got a candidate here. Let's try this. Lambda x u applied to u. That looks pretty simple. Hard to believe. I'll just type it in. Hard to believe we wouldn't be able to type check that. Well, let's build it up. So first of all, lambda u. Let's do lambda u first of all. That's just the identity function. Sure enough, that types. X. U applied to U. Oh wow, why didn't that work? That doesn't type check. Huh. Well, it's that self-application. This self-application of U applied to U, very naughty, very naughty. In fact, we have to be really careful when we have any sort of self-application. We have to add something like fix to the interpreter if we want to be able to handle this sort of recursion, because what we're starting with is basically the simply typed lambda calculus, just those three forms, lambda calculus forms. And in the technical jargon, the simply typed lambda calculus is strongly normalizing. That's just type theory speak for saying that whatever programs that we can type check, those programs are guaranteed to not go into an infinite loop if they type check under these rules that we have right now. Okay, so as soon as we start doing things like self-application, which is really at the heart of some of these programs like Omega, like the simplest infinite loop you can write in lambda calculus is lambda x applied to x applied to itself, that term. That term will go into an infinite loop. We can see it won't type check. If I try running that expression just in scheme, it's not going to come back. That is an infinite loop. Okay, so we don't get a type for that because it doesn't have a type in our type system currently. We can add the ability to handle recursion and the ability to handle self-application, but right now we can't type just this expression, and that's either a good thing or a bad thing depending on how you look at it. If you want to make sure, absolutely sure, that your program can't go in an infinite loop, then one way to do that is to make sure you have a type system that doesn't allow programs that go into infinite loops, that will reject programs that go into infinite loop. Therefore, you can guarantee that everything you do will terminate in finite time. It may take a long time. Someone can still build up, ridiculous terms that take, a million years or whatever, but it will come back. But a true infinite loop won't be accepted. Okay, that's kind of that's a very interesting result, actually. So we would actually have to extend our type system if we wanted to handle like recursion, things like that. Okay, Orchid wants to run it backwards. That's a really cool idea. Let's try running it backwards. So let's try, for example, let's do a run one. Let's give a type. Let's give an arrow type of, I don't know, a arrow a. Okay, this is the type of the identity function. Underscore 0 arrow underscore 0. Let's see if we can find function or a term that has that. Yeah, sure enough, lambda xx, or this is equivalent to like lambda xx or something, right? This is the identity function. In fact, I can run this in scheme just fine, and I can show you it really is the identity function. I'll give it 5, and I'll get back 5. Okay. I can ask for a second answer. Is there a second answer? Or is this going to go in an infinite loop? Crickets. The crickets are cricketing. I think there's going to be a billion. I think you're right. But what will they have in common? What will all those billion terms have in common? The thing they have in common is that they're all the identity function. Okay? So here we got something with an if in it, if hash f, and then whatever the variable is coming in is using that in both cases. So that'd be like lambda x if hash f xx, and we know that since if hash f, we're always going to try the else branch, right? This is really lambda xx. This is still the identity function, so we can feed in 5 that, get back 5. Okay, so yes, there are a billion, there are a trillion, there are infinitely many of these things. I mean, I don't know how quickly maybe we can get back. Yeah, so we can easily get back like thousands of these things, I'm sure. Yeah, I'm sure we could easily generate 1,000,000, or if we were patient enough and tried to optimize things and parallelize it, 1,000,000,000 of these. But so like, let me take this term here that we just generated by running backwards. That term here is the identity function. If I apply this to 5, I get back 5. I don't even have to look at what the body of it is. I know it's the identity function because the only type, or the only types of the only expressions in our language that are going to have this type are going to be the identity function. Technically, things like omega can also have the anything arrow anything type. New programs that diverge, but we're rejecting those in this case. So what's going to happen is we're just going to get back, bigger and bigger, more complicated programs that are all equivalent to the identity function. Okay. And there's a whole very interesting aspect of theoretical computer science devoted to what's called the Curry-Howard isomorphism that talks about the connection between the types and these terms or expressions that have those types. So now we're starting to do things like give types in our code, right? We could also do it with like a simple type like an int. Give me 1,000 expressions that have type int, right? So apparently that expression, so let's see, _0, that has to be a number. I'll stick in a 5 there. 2 has to be a number according to these constraints here. I'll put in a 2 there, or 3. This has to be a number. I'll put it in a 5. This has to be a number. I'll put in a 7 or an 8 or something. And sure enough, we get back a number, right? These are, we have the ability to ask for terms of various types now. And this connection between the types and the terms of the expressions, there's a connection, a strong connection between that and proofs and propositions in logic. Okay, so this is called the Curry-Howard isomorphism. It turns out that they are strongly related indeed. They really, our proof checker really is the theorem prover, or a proof inferencer, or type inferencer is the theorem prover. Type inferencer is the theorem prover, and when we run it backwards, we're asking for a proof that a certain type can be inhabited, that a certain type exists. And the program we get back is a proof that the type exists. Okay, and in fact, modern proof assistants, things like Coq and so forth, they use this idea of trying to inhabit or find a type or an expression or a term that has a certain type. That's the basis of their proof mechanism. So this is a very powerful and very modern way to look at theorem proving, is through type habitation, where you give a type and try to find a term that inhabits that type. Okay, so ORCID wants us to inhabit a type. Okay, so let's see if I can type. So ORCID, you just want me to run that backwards? See if we can get that type going. All right, so ORCID gave me a big type, and I'm assuming this is a syntactically legal type. And apparently this is an expression that inhabits that type. Okay, so A arrow B arrow B arrow C arrow C. Oh, okay. Very good point. Very good point. What ORCID is pointing out, that this is a proof. This is the same proof that we started the Hangout with, right? with Matt Might's proof checker, right? So we had assumptions. We assumed A, we assumed that A implies B, and we assumed B implies C, and we were trying to prove the theory that C holds, right? And so now, by running the type inferencer backwards, we can treat the type inferencer as the theorem prover, and we can find a proof that actually holds, that we can derive C from this. Okay, so if that's right, then if I change C to something we can't prove, like shouldn't be able to prove D from this, look what's happening. It's not coming back. Okay. Now my guess is this is probably going to run forever. Probably just not ever going to be able to prove that there is no type that inhabits this. I'm not sure. I mean, I guess in theory, I mean, we're running into the Holding problem here. We could let it run for a long time, and maybe it'll come back and say there is no proof. But my guess is this is an infinite loop. And that can definitely happen in miniKanren programs. When we try to find an answer that doesn't exist, it might go into infinite loop instead of terminating right away. But if we ask for a proof of something that holds, miniKanren should find that. Okay, yeah, so that's a great example working. We're showing that we can use the type inferencer as a theorem prover. Any questions about that? This stuff's really cool, really deep. Benjamin Pierce has a book, Types and Programming Languages, that types and programming languages, TAPL, T-A-P-L, that goes into this in lots of detail. There's also a Phil Wadler paper, Theorems for Free, I think, is the one that goes into this, the Curry-Howard isomorphism, and he's got a nice paper describing sort of the connections between the types and theorems and propositional logic, basically. Theorems and propositional logic we might want to prove. So this is really deep, really cool stuff, and to me what's really interesting is how easy it was for us to basically just add the rules to miniKanren. I think the miniKanren rules are about as short as the math. Maybe sometimes if we use the pattern matching, it'd probably be shorter than the math rules. And I don't know how much further this can be pushed with the type inference. Some typing rules get really complicated and they're not so easy to express probably. But we can also add things like Henley-Milner has a form of let called polymorphic let, and it's possible to add that. Just basically, this very similar in a sense to adding let rec to a relational interpreter. So you can add things like polymorphic let. It requires bigger changes because the way you change you have to change how the environment's handled. Now you have a recursive environment and a non-recursive environment. That's one way to do that. But you can write that in a way that's purely relational, and you can do type inference for Henley-Milner running backwards and those sorts of things. Yeah. Okay. So that's all I had to say about that, and I will stop my screen sharing. Yeah. So that's the world of type inference. It's very interesting. I wish I knew more about it. I know a little bit about it, but yeah, that's kind of like the very tip of the iceberg, right? I mean, there are many people who spend their entire careers like studying type systems like this, and in fact, to a large extent, modern functional programming language research has largely become about types. Not completely, but largely. So. It's cool stuff. Languages like Scheme or that don't have a type system, like languages like or don't have the same sort of type system that happens at compile time, type checking. Those have fallen out of favor, certainly in academia. Although one cool thing that has happened, and what the sorts of things that Ambrose works on, is trying to get the benefits of both the type system and the nice aspects of having a very dynamic language, like Python or Scheme or whatever, where you don't have to write any of the types down. And so there are various approaches to that. There's gradual typing, soft typing, and so forth. And Ambrose has worked on typed closure, and he's working with Sam Tobin-Hochstadt on typed racket. Sam's been working on typed racket for a long time. So Jeremy Seek at Indiana has been doing gradual typing work for a very long time. So there are a bunch of people who are very interested in trying to combine type systems, type inference, all sorts of things like that, with languages, or add those to languages that traditionally haven't had a strong type system, but in a way that's not too obnoxious for people who don't want to write types down. So that's a very active area of research right now. So there's historically been these big wars in the programming language community about, do you want a strong statically typed language? And Bob Harper is going to get mad at me for using those terms the way I did, but I'm going to use them anyway. Do you want to use a language like ML? Do you want to use a language like Haskell? Or do you want to use something that's really dynamic, something like Ruby, something like Python, something like Scheme? And I think this cool recent work is that, well, you don't have to decide one way or the other. You can have the advantages of both through things like gradual typing. All right. So I've spoken a lot today. Okay, Orca says, I feel like types is just one thing you can analyze about programs, but people think it's everything. Yeah, I mean, I've got a little bit of that feeling myself. I think types are very interesting. I think there are things that aren't types that are very interesting. And I think academic programming languages in general, we tend to forget the fact that there are trade-offs for everything, and there are reasons that people want different languages, different approaches, and things like that. There are some cool approaches. Dependently typed languages are very cool because then you can express Turing-complete properties in the type system, or at least very rich type properties in the type system that go way, way beyond what you can do in something like Hindley-Milner. So, one view is that maybe the type systems we've had in languages like ML are just way too weak, and that's the reason that they feel too restrictive. Once you really get into the really powerful type systems, then the type inference or type checking, you can get into undecidable problems because you can express arbitrary computation. I've got no problem with that. I've got no problem with infinite loops, obviously, as a miniKanren programmer. So I think that's fine. That's a reasonable trade-off, but it is a trade-off. And then there's also things like the gradual typing, which is another set of trade-offs. So I think there's more than one way to do it, and I'm happy to see that people in academia are playing around with different ideas for typing now, and hopefully that the kind of holy war attitude will subside because I don't think it's healthy. Yeah. So yes, a COQ is a proof assistant that's being used a lot for improving properties of our programs, and it uses these dependent type things. Very, very powerful type system. It's basically using type habitation, except the human is guiding it instead of doing a search like miniKanren does. Sometimes you do a search, and sort of mixture of human guidance plus a search so you can handle bigger programs. Idris, yeah, Idris. Idris is a very cool language. Agda. There are a bunch of these languages with dependent types that are really cool. Some of them are being used primarily for proving properties of things. Some of them are being used for just general programming. But yeah, those are really neat systems. Very neat systems. And I'd like to see more about how you could combine things like Idris with logic programming. There are lots of cool connections there. And some people have done work on this, dependent types and logic programming. And if you look at like 12th out of CMU, that's a really cool system. Okay. Does anyone have anything they wanted to show off, or is there any hacking, pair programming things we wanted to attempt? Or shall we turn it off? Shall we end earlier? This is too much for a single session. It was a lot. This is a lot, right? This is like a super brain dump. That type system stuff is hardcore. I mean, we covered what Dan covers at Indiana University over, I don't know, a week or week and a half in the last 2 hours. Yeah, we've only been here for 2 hours. That's right. So one thing I could do is check in the code and let you all play around with it. But one thing that'd be really cool is, if we could do a theorem, a type checker, just in Racket, and turn that into a type inferencer by putting logic variables in the right place. I think that'd be really neat. Yeah. So anyway, yeah. So I guess Ambrose was going to join us, but he was having some sound issues. So I guess we're not going to do epic type coding session, which maybe for the best. But now that we know the basics of type inference and typing rules and type systems, then we can maybe play around with this another time. And I thought that was really nice, Orchid, that you showed that we could prove the same things that we wanted to prove with the type checker in miniKanren using we're using the proof checker as a theorem prover, and we were able to prove the same theorem in miniKanren using the type inferencer, right? So that's a pretty strong proof that there's a connection there, right? We really are using type inferencer as a theorem prover. That's really neat stuff. Yeah. Well, given that spring break and I do have a paper deadline coming up, I too am not going to complain too much about only a 2-hour hangout, especially given how much we covered. But yeah. So I know some of the folks who maybe otherwise were going to show up because of spring break, they're not showing up either. So this is kind of a lightweight one, but that was really cool stuff to know about. The type inference stuff I think is really neat, and hopefully if you've wanted to know about type inference or want to play around with it, this gives you a better idea. So and anyone interested in reading types and programming languages, this is fun stuff to experiment around with. And to me, it was kind of a big eye-opener to realize that I could take these rules and just type them in and have them work and play around with them. That gave me a sort of I don't know how to explain it. Felt like it gave me more intuition and easier. I could just look at that as code now. Seemed less intimidating. So I think that's fun. Alrighty. Well, I need to get to working on my paper about miniKanren. So thanks everyone for joining. And this is we should do a types and programming languages read along. Yeah, a lot of people are doing that. When I was at Hacker School, for example, a lot of people were doing that. It's kind of a big book. And originally, our previous footage is available, like previous Hangouts. Yes, they're on my YouTube channel. Code is less intimidating than math notation for some reason, except for I think the code feels less intimidating because it just feels more concrete. And also the other thing is that mathematicians and logicians, they can sweep stuff under the rug, right? Like as Orchid pointed out with the variable capture and shadowing, like that's actually a really tricky issue. And sometimes logicians or mathematicians will just say, well, we assume this convention or whatever, right? But it turns out that that's actually really tricky and subtle. So implementing stuff, I think, is useful because it'll help you understand it better, help you understand the side conditions, and sometimes it's just wrong. There's a paper on a type system for security that I read maybe a year and a half ago, and I had a bunch of these typing rules, and I didn't understand them, so I typed them into miniKanren, and I couldn't get all the examples to work. So I wrote to the authors, and sure enough, there was an error in the typing rules. So I thought that was That was pretty cool, right? Let's see. Yeah, Hangout. Last week's Hangout's not up yet. Hopefully, I'll get that up soon. The thing, if you try to do in Prolog, you don't have disequality constraints. I used member and I got bugs, as Orchid is saying. Yes, so having disequality constraints is really useful for the environment lookup. The other thing is that standard Prolog search is depth first, so that also isn't as good for type habitation. So miniKanren, I think, is decent for this sort of task. Another thing to look at, another system to look at is Alpha ML, I think, is the name that they finally settled on. Matt Lakin's system that he did for his dissertation out of Cambridge with Andy Pitts, who invented nominal logic. And that's a logic programming system based on nominal logic. There's also Alpha Prolog, things like that. Those are also really good systems for writing these sorts of programs. But once again, I don't know if their search is depth first or not. So miniKanren's basically at this point a language optimized for writing things like interpreters and type inferencers as relations. So it's pretty good at that. I'd like it to be a lot better, but you know, if you just start with a minimal Prolog system, I think you're going to have trouble getting this far because that's not necessarily what Prolog is designed to do. You can make it do that, but miniKanren, we have a bunch of special constraints and things like that, like Symbolo, just to make it easier, and disquality constraints. Well, actually, I should take it back. Many Prologs do have disquality constraints, so Orchid, you might want to check to see if your Prolog has disquality constraints. Many of them do. It might even be part of the standard. I'm not sure. This was Sussman's opinion also. Implementations as didactical tools, yes, and Alan Kay has also said this, right? We build things to learn, right? So it's sort of like a very constructivist approach to trying to understand something is you implement it. And in fact, someone yesterday wanted to understand something about continuations, a paper by Olivier Danville on continuations, and we were, this person asked me over instant messaging if I understood this paper, and I'd looked at it, but I didn't remember all the details. So what I did was I just implemented it all in Scheme in I don't know, half an hour or something like that, and got it working. And then by the time I was done with that, I really understood it much better. There were a couple things I didn't understand until I implemented it and played around with it. So yeah, implementing things is a very powerful way to understand something better. You don't need Prolog anymore. Well, no, I got nothing against Prolog. You can do some stuff in Prolog, but I think the search in Prolog is probably a bigger issue than the lack of disquality constraints, because there are plenty of Prologs that have disquality constraints, and plenty of Prologs with different search. But I think it's also the case that because miniKanren is specifically designed to write these sorts of programs, that it's probably a little easier, probably get better performance. But there's a lot we can do for miniKanren to make it a lot better, right? More expressive, much faster. So we shouldn't pat ourselves on the back too much. Although I am really cool. I think it is really cool that we can start writing real racket programs and treat those as relations. To me, that's really exciting. That's really neat stuff. I'd like to see how far we can push that. I would love, for example, to write an abstract interpreter in that style. I think that'd be neat. Okay. I think that's it for today. Kind of lightweight session. Only 2.5 hours is lightweight these days. But anyway, thanks everyone for joining. Have a great week. Have a great 2 weeks, because next week is spring break, so no Hangout. This week's spring. Next week I'm going to be in Los Angeles visiting family, and then come back and do it afterwards. Also, I've got that paper deadline, so I'm trying to protect my time. But anyway, see you all in 2 weeks, and I'll check this code into the Hangout repository in case people want to play around with it and play around with the type inference. It's a lot of fun. Yeah, so very cool. All right, yeah, thanks for well wishes for the paper, and if anyone wants to read the paper, let me know. I'm happy to send you a draft. Yeah. All right, everyone, have a great 2 weeks, and I will see you all soon. It is an OOPSLA paper. It is an OOPSLA. Okay. Bye.